So we come to 11.6. I told you it was coming. Combined gas laws. We've seen all these relationships between Boyle's law and Charles' law and Gay-Lussac's law. Now combined gas laws. And I hope during the course of this you were starting to notice, there's these relationships. There's direct relationships and an indirect relationship. But in the back of your mind, I know you were thinking, man, somehow this is all going to come together. And this is where that actually happens. So, learning goal, use the combined gas law to find the final pressure, volume, or temperature of a gas when changes in two of these properties are given and the amount of gas is constant. Still, we need the moles to be constant. But with that relationship, as long as the moles are constant, we can find other things. So we are going to be dealing with three variables on each side of the equation at one time. So a total of 6 variables, meaning there are 6 iterations of this equation. All right? All right, let me get my handy dandy pen. Okay, cool. Combined gas law incorporates all pressure to volume to temperature relationships for gases previously studied. It is useful for studying the effects of change in 2 of the variables on the 3rd variable while the amount remains constant. Remember, moles don't change, so the amount must remain constant for this to work. All right, so we got P1 times V1 over T1 equals P2 times V2 over T2. No changes in the number of moles in the gas. All right, so if we look at this combined gas laws, what they're saying, properties held constant. Okay, all the n's, remember, are moles. Okay, so in every one they have to remain constant. But these are base formulas. Okay, Boyle's law, Charles' law, Gay-Lussac's law. If these one properties were to remain constant, this table right here would be very handy dandy for your notes. Okay, it's something to refer to depending on the kind of questions that you're going to get. So I definitely would stress getting to know these and really writing these down and understanding how they work. All right, so here we go. Helium gas has a volume of 0.18 liters at a pressure of 0.8 atmospheres and a temperature of 29 degrees C. At what temperature? All right. Well, these gases have a volume of 90 milliliters and a pressure of 3.2 atmosphere. So notice that we're dealing with 6 variables. We're given 5. And we're searching for that last one. Excuse me. So, in that case, we know we can solve. We've got 5 out of the 6. Now it's a matter of manipulation of the formula. Okay, first thing we do, got to organize the data. Our P1 is the 0.8 atmospheres. Our V1 is the 0.18 liters, and the temperature is 29 degrees Celsius plus that 273 Kelvin, giving us 302 Kelvin. We're going to 3.2 atmospheres and 90 milliliters, okay, of volume, and then we're looking at temperature, all right? Now I want you to notice up top we have 0.18 liters. Down here we have 90 milliliters. So we also have to deal with the fact that the liters, the volume, okay, has changed as regards to designation. Off the side, they did put in parentheses, and you always want to convert as quickly as possible. That 0.18 liters equals 180 milliliters, okay? So let's see where we're going to go from here, all right? So we're looking for T2. So we know that P1, V1 over T1 equals P2, V2 over T2. So they stand it up, so it's all multiplication. So if we look at this and we're looking for T2 right here, all we have to do to get T2 alone is divide by P1, V1, okay? That'll cause that to cross out. If we do it on one side, we have to do it on the other, but rather than my poor penmanship, there we go. So T2 equals P2, V2, T1 over P1 V1. All right, simple enough. So now, plug and chug, man. We've got our setup on our formula, and I find most of my students in engineering, actually, it's always that setup of the formula. Once you have the formula, it's plug and play. But you got to set up the formula. And that's why algebra is so important. All right. So 3.2 atmospheres times 90 milliliters times 302 Kelvin divided by 0.8 atmospheres times 180 milliliters. Cross, 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 cancel, cancel. And what are we left with? Kelvin, because that is actually what we're searching for, so it makes sense. So we multiply the top, we multiply the bottom, and then divide the top by the bottom, okay? That gives us 604 Kelvin, all right? But we want it in Celsius, so now we have to subtract out our 273, giving us 331 degrees Celsius. Pretty straightforward. Okay, so gas is a volume of 675 milliliters at 35 degrees Celsius and 0.85 atmosphere. What is the volume of the gas at negative 95 degrees Celsius and a pressure of 802 millimeters per mercury? Okay, of mercury. All right. A little more complicated because we're going to have to take atmospheres to either millimeters of mercury or millimeters of mercury back to atmosphere. But since we know 1 atmosphere equals 760 millimeters of mercury, conversion is pretty easy, okay? And it says, what is the volume in milliliters? So we know that's constant, all right? So first step, organize. Write down the data that we have. Do our conversions where we can. Now you notice here they chose under, if I can find my little pointer, where'd it go? Under the conditions, I can't find it. Anyway, P2, they've actually changed that to atmospheres, okay? Easy enough, right? 802 divided by 760, 1.06 atmospheres. All right, we got constants then. All right, now here, we want to get, what are we looking for? Okay, what is the volume, all right? Volume 2. So volume 2, okay, is basically what we want to get alone. So how can we get alone? Well, if we divide by, I didn't mean to do that. So if we divide by V2, bring that down there, and, oh, hey, we don't want to divide by V2. I apologize. I forgot what we were looking for, so let's just erase that. Okay, so instead, if we divide by P2 down here and multiply up by T2, that is going to give us, it's going to leave V2 alone, and so that becomes P1 times V1 times T2 over P2 times T1, finding that second volume. All right, we got a formula, we've got an organized chart, plug and chug, right? So 675 times 646 times 178 over 802 times 308, okay? And if we multiply the top, multiply the bottom, and then divide the top by the bottom, we will be left with 314 milliliters, all right? We found the second volume based on the changes there. But remember, we need 5 out of the 6 variables to solve for that 6th variable. So you knew it was coming. We started with, Boyle's law, then we went to Charles' law, then we went to Gay-Lussac's law. Now it's bringing it all together. There's a relationship between pressure, volume, and temperature. And if you know pressure, volume, and temperature on one side, and you know at least 2 variables on the other side, you can always solve for the third.